Hello everyone, I'm Samey and I'm going to talk about linear programming for resource allocation in a public health setting. Okay, let's just dive right in. So let's start with the problem statement. So I'm going to talk about a project in Togo, which is a small West African country. And like most West African countries, it has a really high fertility rate of about 4.26, which is basically like the average number of like children that a woman will have. And that's like twice the average global fertility rate. And mostly high fertility rate means closed-space birth. And what does that mean? That means that could like lead to issues with both the mothers and the children. And in most third world countries, a high fertility rate is due to low access to contraceptives and to family planning resources. And the governments and different NGOs are working together to improve the contraceptive distribution as well as access to family planning. So in order to do that, they implement various programs and to distribute contraceptives in the country. And one of them is the kind of interventions where they can distribute those contraceptives. And usually they have two strategies that they use to distribute the contraceptives. The first one is open days. And at these open days, they will just allow women to come to the district hospital to get contraceptives that they need. And they also have a second strategy, which is mobile strategies, where you have health workers that will go and distribute those contraceptives to women in remote areas in the country, in rural areas. And they can have these different strategies and have interventions that can happen ideally 4 times a year, but sometimes less, depending on the funding that they have. But in the past years, they have noticed that they haven't been able to reach the coverage, which is the number of women they covered with these interventions. As an example, in 2022, they were able to only reach 26% of the women, but they had a target of 35%, which is in terms of women that were covered by those strategies. So they reached out to us to help them first make those strategies more cost efficient and also allow them to reach the target coverage. So before we understand why they were not able to reach the coverage targets, let's take a look at how they will plan those interventions during the year. So ideally at the beginning of every year, they will, based on intuition, try to look at a number of open days or mobile strategies that they can implement during the year. Then they will apply those strategies to every single district, regardless of if those districts are more rural or more urban, or regardless of the size and the population of those districts. Then they will just calculate the budget, and if the budget is approved, they will implement those strategies. If not, they will go back and try to update the planning and then go through the same process until they get approval. So you can already see the issue with that, right? Every district has different specificities. Some of them are more urban, some of them are more rural, some of them have big population, some of them have low population, and using the same combination of strategies doesn't really make sense. So we need a more tailored solution, and we needed first a solution that will that will improve the intervention planning. How will we do that? We will do that by providing flexible recommendation, meaning that every district has its own specificities, and we need to cover that with the solution to improve this intervention planning and improve the coverage. We also need granular recommendations. So for model strategies, like I mentioned before, they will go and go to to remote areas to distribute the contraceptives. And with the way they will plan it, they don't plan for these areas, which are also have their own specificities. So we needed something that will also cover that while planning for those interventions. And we needed something, a solution that will help also determine where to plan given the number of interventions in the year. So if we plan semi-annually, the planning needs to be different from if we plan every quarter to capture that element. We need also to improve the cost effectiveness of the intervention planning by making sure that we have always the minimized cost or the most optimal cost to implement those strategies within the country. We also needed to plan those adapted to the realities and the needs of the health districts within the country. And we did something that make them able to estimate the budget easily without having to go through these many rounds of calculation. So you're probably wondering how we do that. And I'll start with an example. How would you do that? That approach with classical methods like brute force and a simple algorithm. And for that, I'll give a simple example of, let's say we want to plan those interventions in only one district. So if you want to do that, then we can have two. We can represent like the strategies variable here by the vector x, which is basically representing the possible mix of strategies we need to implement those interventions. And here we have one open day and one mobile strategy. The open days will represent the open days with x1 and the mobile strategies with x2, right? Then we also need first to think about the cost, and we'll represent the cost with the vector m, meaning that if you want to understand that better, that will be that the cost of implementing one open days would be like $3, for example, and the cost of implementing a mobile strategy would be like $4. Then we can represent the coverage obtained using those strategies by the vector a. So that will mean that, as an example, we can like cover like 5 women using the mobile, like the open days, and 7 women using the mobile strategies. Now, let's think about the problem here. The problem here is we need to make sure that we'll be able to cover all the women. And for that, we have a target, like I said, a target coverage here, which is 8 as an example, right? So our first equation that we need to solve is to make sure that 5x1, which is the number of women we can cover if we implement the open days, plus 7x2, which is the number of women we can cover using the mobile strategies, is greater than our target coverage here, which is 8. But not only that, we need also to make sure that we minimize the cost, which here is like $3 times x1 plus 4 times x2. So like I said, we can try to solve that equation using a brute force, which means that we're going to like look at all possible solutions, like calculate those equations and try to find the one solution that will fit both of these constraints that we have. So you can do this one by one. So if you have x1 and x2 at 0, everything is 0, right? So we don't, it's not a solution to our equation. The same thing for if you have x1 at 0, x2 at 1, x1 at 1, and x2 at 0. So here, if you have x1 at 1 and x2 at 2, then you'll be able to, sorry, at 1 also, be able to have a total cost or coverage first. If you look at the equation, which is 7x1 plus 5x1 plus 7x2, we get a total coverage of 12 women. So we have solved the first equation. But here we only have one solution here, and that's automatically the minimum. But if you had many solutions that will solve the first equation, we look at the one with the minimal cost. So you're probably going to tell me that that's a high school level of maths, right? And that's really easy to solve. But let's try to scale that to the use case of the government. So we have here 2 possible solutions, right? Which is 2 possible strategies. And we have 2 possible values because it's a binary vector, right? Which is 0 if you're not implementing and 1 if you are. Then we need, meaning that here we have 2 to the power of 2 possible solutions. That's 4 here, like you can see here. Now we have 39 districts in Togo. You have to multiply that 2 by 39, and we also can implement that up to 4 quarters. So we have to multiply 2 by 39 and also by 4. So we get 312. So we have 2 to the power of 212 possible solutions. So that's approximately 2.22 times 10 to the power of 93. So even if you have 10 billion high schoolers and we give them like 10 billion years, they probably won't be able to solve that. So we could also have used different algorithms, but most of them either will be too slow or will not help reach the optimal solution. So we had to find a way to be able to reach the optimal solution and to be able to speed up the process. So let's talk about what we did and talk about linear programming. Is anyone familiar with linear programming here? Okay, that's nice. So for anyone that's not familiar with linear programming, it's basically a mathematical method that's used to find the best possible outcome, which can be the maximum profit or for like finding the minimum cost, subject to a set of linear constraints that define the problem. And now let's try usually we have like 3 components if you want to implement a linear programming model. First, we need to have the data, which is basically like the set of values that define the problem, right? We also need to have the constraints, which are like the linear constraints that also define the problem, and to have an objective, which can be minimizing something or maximizing something. Now we can try to like apply linear programming to to the example that I showed before, and this is the formulation of that same problem we had before using linear programming. So here we want to minimize 3 times x1 plus 4 times x2 under this constraint that 5 times x1 plus 7 times x2 needs to be greater than 8. You also introduce 2 more constraints here because we need x1 and x2 to be greater than 1, right? Because you have binary values. So we can just, since you have only 2 variables, we can just try to represent that on a plane here. And that's the representation. So you have the line in green, which represents the fact that we want x1 needs to be greater than 1. So we use this line, which is x1 is equal to 1. The red line is x2 is equal to 1. And the blue line represents our constraint, which is that we need to get a coverage that's greater than the target. So now this intersection is our feasible region, meaning that most of every point here can basically solve our problem, but it's not enough. We need to be able to minimize the cost as well. So there's a linear programming theorem that says that the best solution that will fit our objective is always on the corner point. I won't dive deeper into that, but you feel free to do more research to understand that. Meaning that now we reduce the space to only 3 possible solutions here, which are like the corner points, and we can just find the one with the minimal cost, and you can see it's the one here with x1 equal to 1 and x2 equal to 1. So here we will be able to minimize or reduce the number of possible solutions. And of course, here only have 2 variables, but at scales, you'll have less and less possible solution and just have to get the one with the minimum cost. And that's how linear programming works. So first we get the feasible region based on the constraint that we have. Then we go and try to find the solution within the feasible region that will minimize the cost. Now, why is it the best solution for the government when they're trying to implement those interventions? First, it's because we're always going to get the minimal cost given the problem that we have. So they wouldn't have to go back and try to update the budget every time they get a set of recommendations for the strategies to implement. And also, it's a more objective way to plan the interventions. Before, they'll use only intuition to try to plan, and they'll plan everything for for the district in a data informed way. Also, we can it's also parameterizable and flexible, so we can give them recommendation for every district rather than one that they will apply for all of the districts. And we can reuse this solution with minimal changes as well. So now let's try to look at how we implement that using code, right? So to implement it, we used Julia for different reasons that I will explain later. So if you want to implement this example using Julia, it's pretty simple. We need to import the jump library, which is the Julia library that we use to solve linear programming problems, and also the CBC here, which is an optimizer, basically optimizers are a set of algorithms that we use to solve our linear programming at scale. So here we just need to instantiate the model here, get all of the variables. Here we only have 2. Get the objectives, which is to minimize the cost. Get the main constraint here, which is to make sure that we reach the coverage target. And here we don't have to add the other constraint I've added, because here we've set the x1 and x2 as binary variables. Now we only have to optimize that linear programming model that we instantiated and get the result, which is pretty simple. So now that we understand how to implement a really simple linear programming model, let's try to generalize this solution to the one that we implemented for the government. So this visualization kind of represents the linear programming model that we just built for the government. And we can clearly see the 3 components here, which is the data, the objective, and the constraint. So let's try to look at these components one by one. So here we have the data here, which basically is the data that we use, and that has all of the information that we have applied to get the cost and the constraints. But first, we need to have the strategies variable that we are trying to optimize. So to generalize our solution, we don't have 2 variables here. We have a matrix of size L times T, L being basically the total combination of possible intervention to plan all over the country. So it can be it's typically 1 open day for a district. It can be many mobile strategies for 1 district, depending on the number of health areas. And then we have the T, which is the number of columns, which can be up to 4, because we can plan this intervention every quarter, 3 times a year, twice a year, sometimes once, depending on the use case of the government. And of course, the binary matrix, meaning that all of the values inside the matrix are binary values. We now have the coverage vector. So instead of 2 values here, you have L values, which also is the number of combinations of strategies within the country. Here we only have a vector because the coverage ideally wouldn't change no matter the quarter. Also, we have the cost vector. Here also, it's basically the cost to implement each of the strategies. Same way, we only need a vector because the cost stays the same. Now let's talk about first the objective that we have. Our main objective is to minimize the cost. And here's the representation of objectives, which is in mathematical terms, we need to minimize the sum of the cost vector and the sum of the product of the cost vector and each column of our matrix. And in plain English, that's basically make sure that the total cost is as minimal as possible. And then we have the third component, which is the constraints that we have. And again, we only have 1 constraint. By generalizing, that's the representation, meaning that the sum of the product of the coverage vector and every column of our matrix needs to be greater than our target, which is A here, A target. In plain English, let's make sure that the total coverage is greater than our target. Now, when we get after implementing these 3 components, we just can pass this data to the linear optimization model that will optimize it and return that matrix with all the values that we need, which is where to implement each of those strategies within the country. So here, for reference, that's the representation of the mathematical representation of the model, which is to minimize the total cost under the constraint that we need the total coverage to be greater than the target. So of course, we can't give them a matrix as a deliverable. They won't be able to use that. So we try to visualize our output as a map here. So we have the map. I don't know if it's visible here. We have the map of the country. And in red, you can see where to implement. Here we have the open days, and here to implement each open days for the first quarter. And the output for the open days will be this, which is 4 maps for 4 quarters. Same thing for the mobile strategies, which will be also where to implement it on the map. And that's more easy to help them like easily visualize the outputs of the model and help them plan those interventions. So now, how did we build that? We built this tool using a combination of Python and Julia. So we used Julia to build the actual optimization model. Why did we use Julia? Because of its syntax, it's much easier to write mathematical code using Julia, especially using a jump library. And also the jump library, for those who don't know, is, I think I mentioned before, the library that we use to build optimization model. So why is it a good library? Because it's much faster than any library using Python, and also has a vibrant community that makes it easier to build and debug this kind of optimization model. And then why did we use Python? We use Python to build the whole pipeline because it has powerful libraries for data manipulation and data analysis, and also because of its powerful data visualization solution as well. And of course, Python is easier to deploy, and also we found a way to integrate Julia code within Python, so that was the best way to implement that and the easiest way to do it. And ideally, to implement code, there's this library called Julia in Python that helps run Julia code within Python. So that's how we built this whole solution. And of course, we had to make sure that this model that we built is actually helpful and is better than the way they've been planning those the interventions in the past manually. So what we did is we looked at the interventions that they planned in 2022, looked at the cost, and looked at the coverage that they were able to obtain, and we tried to get that target coverage and put it into our model, and then try to compare the total cost obtained. So here we can see that on the left, our cost is 40% less than the cost on the right, which is the planning in 2022, meaning that with the linear programming, we're able to reduce the total cost. With the same coverage, we were able to reduce the total cost up to 40%, which is a great number and definitely means that using linear programming can be useful to the use case of the government. So building this solution hasn't been easy, and we learned a lot while building this. And I just want to share what we learned so that if you want to build this kind of things, you have that in mind. The first thing we've learned is that implementing an optimization model requires many iterations. So I just showed the final model, but first you had to go through a lot of models to be able to have this one that actually fits the use case of the government. And also, under resource constraint, a simple model is usually better. So we also, like I said, we built many models. Some of them were more complicated. For example, we built a model where instead of optimizing on the global level, on the country level, we'll optimize for every single district and then get the sum to get the total value. We also try to maximize the coverage given the fixed cost, which try to add more constraints, which are basically like trying to limit the number of interventions you can plan within a year, and also limit the number of open days as well as the number of mobile strategies that you can plan within a year. But usually having more constraints means that you limit, if you go back to the graphical representation, you limit the space of feasible region and definitely limits the optimal value that you're able to obtain. So for the use case of the government, a simple model was much better. Third thing that we learned is that to be able to make this kind of project successful, we need a tight collaboration with the government, and not only like people at the head of the government, but as well as the people that are actually implementing those things, to be able to understand the use case and make sure that the product that we build is actually useful for the government as well as the implementers, and also for the population. So let's look at the team that built this. So At ID Insight, we have a mix of data scientists, economists, as well as project managers that helps connect with the government. Here's the team that helped build this solution. So I work at ID Insight, which is a non-profit that has as a goal to improve lives using data. If you want to learn more about what we do, feel free to scan this QR code to go to our website and know more about what we do. Thank you very much.